Hi, everybody. My name is Jeff, and here's my friend Jithender. And today we're going to try to make the case for showing how adaptive routing and switching is a pretty optimal solution for today's AI networks. And we're going to go over sort of the effort to get that into SONiC and sort of the overall design. And here's some mandated legalese from our friends at Marvell Legal. And once you agree to trade in your firstborn, we'll move on. Just kidding. Basically, today we're going to go over sort of the current state of AI ML workloads, sort of the gaps that traditional load balancing has, and how ARS sort of fulfills those gaps. We're going to go over some of the packet flow and the design within SONiC for ARS, as well as a real world example of how to use how we showed it in our lab, as well as some key call to action and key takeaways. So basically, in today's AI ML workloads, it is very different from our standard data center network basically traffic patterns. Basically, we have really high network utilization. On average, probably 95%. And then the link loads actually increase very rapidly. And basically, when you basically scale up to continent-wide basic data centers, you have tens, hundreds of thousands of these XPUs, GPUs running, all doing all communication. And basically, any sort of congestion or even like a fraction of a percent of drop will cause huge idle times with your GPUs. So basically, having really good load balancing is actually a pretty critical thing to basically keeping your GPUs and XPUs humming. And basically, job completion times and tail latencies are key metrics to make sure that we want to keep those as low as possible. So basically, within traditional load balancing, such as ECMP and lag hash, they're all, as you know, probably perform statically in the switch data plane, and we usually match on the typical 5-tuple. But the problem with static hashing is that it doesn't really take into account any of the real-time path conditions, either local or end-to-end. It also doesn't take into account basically the size of the flows, the duration of the flows, or anything like that. And once the path is chosen, our packets are locked to that path. So basically, especially with today's AI workflows, which is basically very, they're usually elephant flows with where the hash is basically has a lot of hash collisions. Basically, traditional ECMP lag doesn't really measure up. It causes a lot of hotspots, and traffic drops and so forth. Another option is using traffic engineering, but that requires a control plane, which is slow to converge. And if something happens, you might black hole some traffic. So basically, we want to make the case for adaptive routing and switching. Basically, with this methodology, you basically would dynamically select the best path depending on your real-time network conditions, based on the past and future load qualities and quality metrics, whether it's queue or port or level or so forth. And basically, we want this. The plus side of this is also the fast convergence, since there's no control plane interaction as well. And the approach of ARS is basically to mitigate congestion and optimize resource utilization, and basically to keep all your XPUs and GPUs humming. So basically, before we get into the nitty-gritty details, we wanted to go over some basic terminology so we're all on the same page. Basically, we have something called a microflow, which is basically identified by our standard 5-tuple, which is usually the single traffic flow. And basically, a group of microflows are grouped within a macroflow of basically those flows are going along the same path. And to divide each of the microflows, we usually have a concept of an idle time. So the idea is that basically after each idle time expiration, you would have a concept of a flowlet where basically these macroflows are divided within flowlets, and they can switch from one path to another, depending on the idle time expiration. And basically, there's two main methods for using ARS. The primary would be flowlet based, where you have basically using link failure or idle times to basically select the path for the next flowlet. Or the other one is basically more or less a spray based, which is basically out of per packet. You basically choose the optimal path for every single packet on your ECMP or lag group. And basically, there's also a concept of minimal and non-minimal cost paths, where basically you basically have backup path if the primary path is worse than the alternatives as well.
Morning, everyone. So now today I'm going to talk more in terms of the technical details of the ARS. Like when I say the technical details, it's more like the scope will be more in terms of ARS implementation in SONiC. So I'm not gonna deep dive into the ARS in the data part side because this has been discussed and you have been like hearing about ARS in the past and also at OCP. Okay, so the scope for today's talk, what we are going to cover is mainly on the local ARS and how that can be enabled by any user or configured in SONiC, and what they need to be aware when they are configuring ARS in SONiC itself. So there are basically ARS can be divided into two types. One is the local ARS and the global ARS. So local ARS is mainly that the dynamic path selection is within a device and achieved by monitoring the local port link utilization, whereas the global is across the devices, and that can be achieved by exchanging the port data utilization across the devices. And the scope is, as I said, it's to the local ARS. And also I'm going to touch on a little bit of architecture and also the design, that how we will be implementing the ARS in SONiC, and also how a user can configure it. So this is most of you are maybe very familiar about this diagram. I don't want to deep dive into that, but to touch on the high level, just to set the context of the topic for today. So Jeff already had covered macro flow, flowlets, and the micro flow. If you see, you can see the picture right side. There are three flows, micro flows, forming a macro flow that further divided into flowlets based on the ideal time configured. And you see that there is a macro flow table that tracks the micro flows to map those to the next hop destinations and they track their status. This is all about the conceptual and the logical pipeline. So if you see here, so the decision making is like for any NH group. So there are two paths it can take, whether the ARS is enabled or ARS is non-enabled, like not enabled. So if the ARS is not enabled, it takes the traditional way of hash mechanism. And if ARS is enabled, it goes the path that we discussed in the conceptual pipeline path. So the thing here is that the user needs to be aware when they are configuring ARS from the SONiC level, is that especially in case of next hop group, how the next hop group is being handled in the SONiC, either by the route arc or by the NH arc. So certain things they need to be aware of that while enabling the ARS, that I'm going to cover in further slides, because the NH is bind to the next hops and also to the interfaces. So when user wants to enable the ARS on a certain NHG, they need to be enabling on the next hop and also the interfaces. So I'll be covering those in the further slides. Okay, so this is the high level of the architecture in ARS architecture in the SONiC. So there is a new ARS orchestration agent being added to the SWSS, and also these are some of the existing orchestration agents where the changes being done to support the ARS in SONiC. So the main purpose of the ARC agent is to for the communication with the DB, and also interacting with the existing orchestrations to achieve the ARS in the SONiC itself, like for the route and NH for handling the NH group and programming those, and for the port for the interface enabling the ARS on the interface level and the ACL. There is a provision to control from the ACL level as well. Okay, so from SONiC level, if you think about the ARS, how to configure it, it is divided into three types, like maybe we call it as the selection mode. So there are three types of selection modes. The first one is the global selection mode. So to configure ARS in the global selection mode, So user has to be programming two tables. One is the ARS object and second one is ARS profile. So first they need to create the object and then bind that to the ARS profile as a default ARS object. So this is going to be a global ARS object bind to that entire system. So all the interfaces part of that system will be ARS will be enabled on all the interfaces. So this is pretty much straightforward in case of the global mode. The next one is the interface mode. Okay, so interface mode, the user can enable the ARS on a particular interface also, like no need to be a global, but can be enabled on a selected interfaces as well. So in that case, the user has to program the ARS interface table along with the object and the profile. So in this case, so on which interfaces they want to enable the ARS, that entry has to be programmed into the ARS interface table, and that along with that, the object has to be bind to the ARS interface in the ARS interface table. So at the same time, they can also have one global ARS object as well, which can be bind to the default ARS object. This can be useful when there is no ARS bound to any specific interface. It can take the global path or global object path. And there is a scaling factor associated with the interfaces that's more to handling the different speeds in the system. Like if a particular interface is of different speed, yeah. And the next one, sorry, going back. So this is almost same in case of it's an L2 or L3, like lag or the NH group. Okay, so the next one is the third mode is the next hop mode. So if the selection is set to next hop mode, so user has to program along with the two default object and the profile and next hops and also the interfaces. So the entries has to be programmed into the next hops and also the interfaces. So the object, when it is created and bind to the next hops, okay, so in SONiC, when an NH group is created by either by the route or by the NH arc, so certain things will be checked, like whether the system really supports. This is applicable for all the modes. Whether system really supports the first thing, system supports the ARS or not, and second thing is whether the ARS is enabled on the particular NH of belongs to that next hop group. So next hop group may have a set of NH, so like 2 or 3. So it is user's responsibility to bind the object to each of the NH belong to that next hop group, and also enable on the interface level that interfaces belongs to that NH group. So with that, the ARC agent in the SONiC that internally validates all these checks and finally programs or enables the ARS in the NH group level. Okay, so one more thing, like if it is L3, there are 3 modes supported. As I said before, like the global interface and the next hop group. In case of L2 lag, there are 2 modes, which is global and the interface alone. Okay, so the next thing is the ACL rule being added to control a specific flow. Like what I mean by this is that this is more granular. So far we have seen a global level, and little bit the granular level is the next one is the interface, and more granular level is the per NH group. So this is like in a NH group, if there are certain flows and wants to control, like not enable ARS on a specific flow, so that can be achieved with the ACL rule. And the action that been added for that is the disable ARS forwarding a specific flow. Jeff.
So next, we're going to show an example of basically a real life experiment we did in our lab. In this case, we basically have a leaf spine topology using 4 TeraLinks 10s connected to a Keysight Aries 1. And we're running basically our KCCB, basically AI simulation software. And we're basically, let me show you the next slide. So basically, without local ARS, basically we got congestion on 2 of the 4 ECMP next hops, and you can see it basically causes a huge long tail, and all the way to like 200 millisecond job completion time, which is no good. But with local ARS enabled, with flow-led based, we can see that basically now all the members are equally hashed, and basically our job completion time drops all the way down to basically about 2 milliseconds with a very short tail. And as always, we always want more feedback, comments, concerns from the community with our pull requests. And I want a special shout out to our friends at Upscale AI who did a hackathon with ARS this past week, and we want to thank them for their hard work on that. And basically, as always, Marvel's been a key contributor to the community. We've been at it for years and years now, and basically, we really wanted to make sure that the community is very vibrant. And basically, we want to push it forward and get it deployed at as many places as possible within the data center and AI ML workloads. Thank you, everybody.
Yeah, I have a question. So do you have data or maybe intuition on what knobs in those objects that would control, parameters of ARS would influence the level of potential packet reordering?
Sure. So basically, for example, if you're running in spray mode, then you're definitely going to have packet reordering no matter what, right? So when you're in flow-led mode, it depends on the specific flows in your network. You have to adjust the idle time per se, right? So basically, if you expect that you have extremely bursty traffic, for example, for typical GPUs, you basically all gather, you all go at the same time. You have a pause during processing and go at the same time. You basically align it with your idle time with those gaps in your network, kind of thing.
So basically, you want idle time to be more than time between microbursts, but less than the gaps between stages of older use, let's say, right?
Yeah, it depends on your workload. So basically, once you figure out how much gaps in between your typical workflows and so forth, you fine tune those timeouts in between. So
yeah, maybe I just say that as a call to action, like for further work. We have pretty good approaches now for PFC headroom and ECN thresholds for them to be dynamic and not, require a specific input from a user. I think this idle threshold would be another one where it would be good to figure out how you can avoid telling the user to choose a value.
Yeah, definitely.
Right.
Yeah, thank you.
Mm-hmm.
Hi, I have seen that a lot of NICs nowadays support the packet spraying. So I wonder, when we have packet spraying, is it still necessary to do this local AIS? Because they will supposedly, so packet spraying will spray the packets across all ECMP passes as well, and you need to handle the reordering either way.
Yeah, so packet spray is definitely a mode you can use within ARS. But I think the majority of the logic we were talking about was basically based on the flow-led base. I think that's the majority we were talking about today, right? So yeah. So packet spray is sort of the, if you really didn't care about packet reordering, packet spray could be an option for your network if you want to go that route. So
okay.
Hi, thanks for the presentation. My question is very much related to the previous question. One of your slides talked about like a disabling ARS on a specific interface. I would like to know what is the use case from the bunch of interface. If you have to selectively disable on a specific interface, is this to reduce the packet reordering sensitivity on a specific port that you're interested in, or is it for a particular destination? What is the use case?
Okay, I can take that. So like you can think about in a device maybe connected to the uplinks, downlinks, and also the storage devices anyway, right? So where the ARS may not be needed on all the interfaces at the same time. So in that case, on a interface level granularity will help to enable or disable on a specific interface.
Just to make sure I got it right, like this is for a specific application where packet reordering is very sensitive. So you identify a flow and disable it on an interface that you expect it to go.
It could be because some places you may not really ARS may not be needed also based on where the port is being connected to. So in that specific use cases, it can be disabled. And also in terms of scale, that can save the with the limited resources of ARS, right? That can also help to efficiently utilize the resources.
Nice. Thank you.
One last question.
Okay, yeah.
So
Offline.
yeah,
Thank you.
thank you.